Okay, hey everyone. Today we want to speak about filter design and how to write your own filters in Rust. So filters are what you know from EQs, right? Here you see what we programmed today. So we have this basic filter curve here that is plotted, and we can change the frequency and we can change the quality. And even we can change the filter type. So if we switch here to bell filter, then you see that with gain we have this nice bell shape, and we can move this around, change the quality, the Q factor, and also the gain. Yeah. Then let's switch back to the, I don't know how to move this here, to the low pass. Dial it in, kind of nice here. Yeah, the gain has no function at the low pass, but the quality. All right, and maybe let's have a listen how this actually sounds here. And now we can add this low pass filter and change the frequency. So that's nice. Then the quality sounds like this. Yeah, can be a real sound design tool here. Yeah, and that's how the filter basically sounds. And the coolest thing is we can modulate it very fast. So if we look at this LFO and set it on the frequency, yeah, you see this modulation here happening. And it sounds very cool when you make it faster. Yeah. So it's a really nice sounding filter here. It's an analog model. And yeah, let's have a look into how to build something like this that sounds so amazing. If we go to first, if you look for filter designs, you will find that there are different designs. For example, the first one you will probably find is the Biquad filter. This is a very common filter algorithm, but it has some problems. So what people usually prefer is something like the state variable filter here. They are both actually Biquad filters, and here you can learn something from Vadim Zavalashian himself. So they are the Biquad filter is more a direct type filter. Yeah, we won't go into math here, and I also am not that good anymore in maths, but you can read something about those state variable filters here. And in this discussion here in this KVR thread, you can learn a little bit more if you're interested. But what the main difference is, if we watch here this talk from Vadim, is that the Biquad filters, they aren't that stable when you modulate them. So you can see here the same thing that we just did here with this fast modulation, and it will sound less good. So let's have a listen.
Is the rate. Yeah. And sometimes we're getting this kind of weird low rumble. And with direct form 2, it's gonna get even funnier now.
So yeah, this is the sound. Yeah, you hear this weird sound, and with the state variable filter design, you don't have it. So maybe as a last memory here, open this up again, play a note. It's always stable and sounds great. So yeah. How do we do this? There's one nice filter design that is very easy to follow by Cytomic. You might know Cytomic from the glue compressor that is inside of Ableton Live. That's actually here his and his wife's work. And there are technical papers here more. And there's one of the state variable filter designs is here. SVF Linear Trap Optimized 2. That is the interesting paper, so maybe let's download it. And here you will see the scratch of the analog circuit that is emulated. And there's the whole mathematical part that is not that interesting if you just want to implement it. So let's go all the way down to here, the algorithm for every response. And that's here the actual interesting part. So there's the clear function that just clears those two states. Those are actually the capacitors inside of the analog circuit. And then you can see the set function that sets the actual coefficients. And those differ from the filter type. So this is for the low pass, the band pass, high pass, notch, peak, and so on. Yeah, there are all the different filter designs, so you can build a whole AQ8 here if you want. And the last interesting thing is the tick function. So this is where a sample, V0, is actually the input sample, and this is the output sample. So after you calculated those coefficients, you only have to recalculate them when a parameter is changed, like the bell, the gain, the sample rate, or the cutoff. And then per sample, this function here is applied. Yeah, I did this already here in a repository. I actually have 2 issues still here that I didn't catch. You will see this here in the issues, what is wrong. But I have a working implementation here in this Rust audio plugin. So that's again our repository where you can see eGUI filter is the branch that is on this state here, if you want to have a look in it. So how does it look in actual code? Maybe let's put this down here again. Thank you. So first, we want to have an error. This is just, in Rust, we handle errors nicely. So here we just have all the different possibilities. Setting the filter could go wrong. And this is just when you set the frequency over Nyquist. Nyquist is half of the sample rate. So if we work on a sample rate of 48K, then 24K would be the maximum frequency we could go with the filter. If we specify a filter, a frequency that is higher, we want to return an error. The other thing is a negative frequency, because frequency is applied as a floating point value. It could be negative. This is not allowed. And also Q is not allowed to be negative. All right, then we can define our filter types we want to support in an enum. Here, I want to support low pass and bell, just as a little example. I just made a filter param struct here to make it a bit easier to set them. But you don't necessarily have to do this. You can also just get frequency, Q, and gain as an input to the function directly. So here I could specify some default values. And then I have my coefficients. Those are the ones you actually find A1 to A3, M0 to M2. You will find here in this paper. Here you see A1 to A3 and M0 to M2. And then the coefficients can be calculated with the filter type, the sample rate, and the filter parameters. So here, at first, we have some guards to just check to return our errors if some settings are wrong, right? And then we can create those coefficients. So this is really just copying this formula. Let's have a look. This is the low pass. You see low pass is cutoff divided by sample rate multiplied with pi, and then of the whole thing the tangent. So let's see here we have frequency divided by sample rate multiplied by pi, and then the whole thing in a tangent. Yeah, so I just copied this code here. Also here, M's are 0, 0, 1, 0, 0, 1. Yeah. So here it's easy to make a mistake. Yeah, read it multiple times. That's what happened to me here. I'm gonna fix this soon. Should be time after 2 years. And yeah, that's how you walk through this. You can implement it for every type you want. Yeah. Now I also took the bell type. And this function, you just call it every time a parameter changes. Maybe you could optimize it a little bit further and check if only frequency changes. You maybe don't have to change everything. Yeah, you have. But maybe in some cases, like for example, if only Q changes, then A1 changes. Yeah, I think you might have to calculate it every time. There's not much room for optimization. Maybe you don't have to set those always, but this is kind of cheap, so should be negligible. I don't know how to say this word, sorry. And then there's our actual filter, so the filter we want to use. Yeah, the filter has filter params. Those are the ones, those are our settings. We don't have to store them here. I did it. The filter type, the sample rate. But what actually has to be in the filter is the coefficients that we calculated and our IC1 and IC2 EQs. Those are the capacitor states. Because a filter always works in a time base, so it stores some of the information of the last samples and applies it to the current sample. So we need some place to store those states inside. And this is just those two numbers. Yeah, and here I just have some nice functions just to set sample rate, params, filter type, and create a filter. So this is not there's nothing special about it. The update coefficients function is called each time we change a parameter, and this will just create a new coefficients object, right? This is real-time safe, as we don't do anything in the new function that allocates memory. And then you see the heart of the filter. This is the actual tick function here. You see V3 is input minus IC2 EQ. Yeah. V3 is input minus IC2 EQ, and so on. This is also just copied here, and this is then our output. So we apply the filter on a sample by sample basis. And then the last thing is the reset function. Just here, the clear, here it's called clear. It will just set both states to 0 again. So we can call this if, for example, our audio process stopped and started again, or some audio settings were changed in the DAW. Yeah, in the plugin you have a reset function as well. There you can call this, for example. Yeah, so you see it's not magic. It's quite easy to do, and the main thing is really just to copy those formulas right, and to write some tests. What I didn't show you yet is the filter response function. This is what I use to calculate this curve here. So this will give for one frequency, the evaluation frequency, a complex output, the response of the filter. So I do this just here for all of the frequencies. I just took 1000 logarithmically spaced frequencies here and just took, for example, 26, then 30, then 40, and so on. Yeah, just calculated all of them and then put them in one line, and I plot this here. Complex is the return type because it can be, it has more information than just the magnitude. What you see here is the magnitude in decibels. So the gain the filter gives to a certain frequency. And you can also calculate the phase out of this complex number. So the magnitude is just the absolute of this number. And the phase is, how is it called, is the, let's see here, complex. In Rust you have two functions, complex and is the argument, yeah? This is the argument, calculate the principal argument of self. This is the phase. And here you also have the function, here it's called norm, but it could also be the absolute. And norm will give you, here you see, this is the absolute self. So norm will give you the magnitude. That's all. And those here, those are a little bit more difficult to get, those functions. They are just, you have to take the function of the filter and then substitute the Zs inside and do some magic, some mathematical calculation to get to this. You will also find this in the internet, or you could also take it maybe from a slightly different filter. But this is now should be the correct mathematical solution for this filter. And then you can just check which filter type you want to calculate. You will find all of them as well in my Simpa filter repository. Okay, so how do we use a filter like this? That's interesting, because the first time I tried it, I made some mistakes with this tick function. Because if we go to our plugin again, the main things that changed is that we now have frequency, quality, and gain, and filter type as a parameter. So we can modulate it in our DAW. And here you see the main thing you need to care about is that you have a different filter per channel. Each channel is an individual audio stream in the end. So you need a filter per channel. That's why we have a vector here, just to get dynamically as many filters as we have audio inputs. And if we go to the initialize function, this is which is always called when audio settings are changed, so also when the audio layout would be changed of a plugin. And here we can get our number of input channels. It's now specific for NIH plug. It will return this as a non-zero, so we have to change it somehow. So we say if the number is non-zero, then we get it, and otherwise we put it to 0 in this case. We just have to transform it into a U size here. And then we can resize the amount of filters we have. So we want to resize this vector to number of channels. And then we will just set all the new filters that are generated. If it's growing, we set this to a low pass. So this is now our default low pass value. And then what we have to do, probably we didn't need to resize if this function is called and just the sample rate is changed. Then this function will also not do anything. But we still always have to set the sample rate for those filters. So this could change every time this function is called. And then I just call this set sample rate. And here, just in case it's a sample rate that is not supported, we can return false. So the DAW knows we don't support this input configuration with our plugin. And in the end, we just return true if everything went well. And the other thing is the process function. In the process function, we get our parameters. So here we get the parameter filter type and just set the filter type. You see here, we iterate over all of the filters and set the filter types for each of them. That's always, you have to check to do this for every filter in the vector, obviously. So also here we set the filter type, and in case it's something goes wrong here, we would return the process status error, fail to set filter parameters. You can do whatever you want here or ignore the error, but this is just a nice way to handle it. And then we go to our frames of audio. We go through the frames, even though it could be less efficient than going through channels. But going through frames will give us the possibility to get the smoothed filter parameters. This is just when we do this fast modulation that we heard before. It could sound bad if we don't smooth those values. And so here we get the frequency, the quality, and the gain as smoothed values. And then again, we iterate through all filters and set those parameters. And finally, we have this filter tick function. So now we have a frame. A frame contains one sample per channel. So the left channel sample, and then the right channel sample, for example. So now in a stereo case, we would have those two samples here. And what we then do is we zip the frame, so left, right, with the filter that is meant for the channel. So now we basically do this, we get the left filter, and the right filter. And we ensured before in the initialize function that we always have for every frame inside of here, for every channel, we have one filter, right? Oops. So now we zip those together, that those are one package and those are one package. So we get this sample and this filter. So then we can call this filter here, ticket with a sample, and apply the filter algorithm to it. And then the next time this loop runs, we do the same for the right one. So that's how it's working. And this is, the first time I think I just tried to tick the whole array and then it just sounds stupid. And you're like, what did I do wrong? Yeah, you need a filter per channel. And here in the reset function, you see we just again iterate through all of the filters and reset them. So there's not much magic. Yeah, it's quite easy if you see it like this, but believe me, there's a lot that can go wrong, and I also needed some tries here again to make it work. So don't be worried if you try it and you get problems. Also, here's still one problem. For example, the frequency. I have it here from 20 to 20,000, and now we smooth it linear, so it would be better if we took a value here from 0 to 1, and then calculate what 0 and what 1 is in frequency terms here, because then the smoothing would be correct actually. Yeah? I didn't do this now. That would be an enhancement that is actually necessary to have the perfect response. But you heard it sounded still kind of good. Yeah. Yeah, that's all there is. Again, here are just the default values. So here I say frequency should be default 500 and then go from 20 to 20,000. Quality from 0.1 to 12. And a gain from -30 to 30. For the Bell filter, it's only relevant in this case. Yeah. Maybe I will show you my OBS here. Let's have a look in how to plot this response here actually with the logarithmic view here. Maybe, yeah, if you implemented it, the first thing is you should check if your filter actually is right. Yeah, so we can have the spectrogram here and maybe change this to a noise sound. Let's try this. And then we can see this is 1.24 kilohertz. Yeah, here's 1.27. So this is okay. Yeah, we go up. Oh, sorry. Yeah, this is at 8 kilohertz now. 8. We go down. This is now at 158, 157. Yeah, so like this, we can check with the noise if our filter works as expected. And also if we change to gain, oh, I don't know how to change it here. Let's put the gain a little bit high. Yeah, you see here as well. Maybe we can change this actually. It would be better if the spectrum that's here is like this. No. Where can we change? The tilt. The tilt, we want to set it to 0, so we have a straight view. And now you see it's straight, and you see that this is here higher. Let's go up with the frequency. Yeah, this is at 1.4, something around 1.4, so perfect here. Yeah, that looks good. And also again with this, now it's not tilted anymore, the spectrum. That's a bit better to identify. Okay, so the filter works. Yeah, you check this, and then let's build this here. So what I actually did is again having an eGUI editor with our editor state here, and we run the editor in our editor function, editor create, and we give our parameters to it as we need to read them to to show the curve here. And then in our editor, The create function is pretty simple. It's just a resizable window with our size. And then we show the filter curve. And the filter curve is just a function, nothing more. It's just a function that gets our UI element, the filter type, and the parameters. Yeah? And you see, I get this here non-smoothed from the values. Yeah, here it's non-smoothed because we don't know the smoothing, the smooth parameters. That doesn't work like this because we don't know the update frequency of our UI here. And the gain we transferred here already into decibels, I think. Yeah. All right, and then the filter curve function is the interesting thing. What we are using here is actually the library eGUI plot. Maybe I can show this again to you. eGUI plot. So this is already giving us everything we need. Try the web demo. Yeah, it's giving us this this nice little graph where we can drag around, have our frequency axis and so on. So custom axis, that's what we are using to generate a custom one with the frequencies. And we can plot things nicely here. So let's have a look. In the filter curve, I actually basically went off from this custom example, yeah, from this custom axis example. You can see here on GitHub the code. And then I saw, okay, for a custom axis, I need a formatter for the frequencies. So here I just say I want to have a line frequency labels at 50, 100, 500, 2000, and 10,000. There are more of those formatters for the different axes. But the interesting thing is here where we generate the response. So I want to have 1000 plot points in this case. We can also take 100 or do this a little bit more smart with getting more plot points around the curve and less plot around the frequency and less plot points where nothing changes. Yeah, but I just go with 1000 here for simplicity. This 300 here I actually just added because I think I have a mistake somewhere and it was plotting stuff a little bit in a frequency range where I didn't want to show something anymore, so I was just adding this here as a little offset to generate only the range that I wanted. But what we do is now we just go from 0 to 1 in 1000 steps. So that's here, yeah, 1000 steps divided by num plot points. And then we get our X position from 0 to 1. And then we want our filter response for this plot position. Scale to log 10 will now just give us the frequency for the value. So 0 would be 20 Hertz and 1 would be 20,000 Hertz and 0.5 something around 500 maybe. So it's logarithmically scaled that you get for each position. Yeah, so maybe I can show this to you better here. So this is 0, this is 1. And this is 0.5 and this is 0.75. Yeah, so we with the 0 to 1 values, we go linear here through this graph, just the position on the x-axis. And with scale to log 10, we just calculate, okay, at 0.75, which frequency do we get? Ah, yeah, 4516. Yeah, that's how it's working. You will see this function here, scale to log 10. Now it's the scaling, yeah, it's basic math. And yeah, so we get our evaluation frequency now for the position, and then we just put in our parameters, which gives us the complex number. So you see now we have a vector with our position from 0 to 1 and our complex number at this position. And then we generate the plot. This is just also copied from the example. So the legend, the spacer, the X and Y axis, blah, blah, blah. Here I want to stop dragging and scrolling in the plot because we always want to show this window. And then I set the plot bounds from 0 to 0.8 actually, because I think, I don't know if there's something wrong with my calculation or with eGUI, with the plotting. And I want to show from -30 to 30 dB. And then we just plot a line, and the line should be from our series, that is the response, yeah, that we calculated here. And then we map this response to be the x position. We just take it like it is from 0 to 1. And our response we want to change here slightly. We want to calculate the norm. The norm is again our magnitude, so the absolute value of the complex number. And then the logarithm from 10 multiplied by 20. And this will just, the norm here is a linear gain value, but we want to have the decibels. And this will just give us the decibels. And then we collect this into a vector and plot it. Yeah? It's a little bit inefficient to always collect this, but this is how eGUI plot works. Yeah? It takes a line and the line needs to be owned. So we always have to generate a new line. Yeah, if this is getting too inefficient, we can also reduce the number of plot points and so on. But you did see, even with the modulation, it worked very fast, and the whole thing is running on the GPU, so it didn't take any performance, not that much performance from our CPU away. What did I say here? I mean, this here runs on the CPU, but still you saw that here the CPU meter, basically has no problem whatsoever. Yeah, I don't think this is a big problem at the moment. But it's always nice to make things more efficient. Go back. And here's just a function to generate our xgrid. Where do we use the xgrid function here? .xgrid spacer. And this is also interesting because the eGUI plot doesn't have an option to just generate logarithmic plots. So again, I set here our frequency lines. Yeah, every frequency where we want to have this line. So I just copied this from other EQs, looked at Ableton, for example, or here at the Bitwig EQ, and just looked where do they put lines that it looks nice like a frequency plot. So it's always 10, 20, 30, 40, 50, then 100, 200, 300, 400, then 1000, 2000, 3000, 4000, and so on. So it looks like this typical pattern, from frequency plots. And then we go to those frequencies and again scale this from log 10. Before we scaled it to log 10 here, and now we scale it from log 10. So we receive from our AT value the position from 0 to 1 in linear values. And then we just say the eGUI doesn't know that we are in those values. It only knows 0 to 1. And then we just push here a grid spacer at the value 0, 0.2, 0.3, whatever. Yeah, and this is how it works. So actually, at first I thought, they don't support logarithmic graphs, but it wasn't too hard with those things. And the formatters, they also just format, they get the value x, so we only get where we are in the from 0 to 1, so we change this again to frequency. So with those scale functions, it's very easy to handle this. Yeah. But I think it's, again, nice compact code. I think the readability is better than at my C++ times because we only have one function here. We don't have any header files and source files. Yeah, it's way nicer to read in general. All right. Thank you very much for watching. And I hope I can do a next video. And the next video, it's a lot of fun, so I can actually finish here some projects and make them look nice. That's a lot of fun. And see you next time. Thank you. Bye-bye.